Okay, so this is our final week of chemistry for this year, which is really sad, but looking forward to the summer. We're going to be talking about neutralization or neutralization reactions. And this is a really important class of reactions that are covered in chemistry classes that involve sort of the properties of acids and bases that allow them to cancel each other out. And so we're going to look at an example problem, and then after I give some notes, I'm actually going to do an example of a neutralization reaction that you might see in a chemistry lab. So here we are. I'm going to start you with this visual problem. So if you can see in this image in the top right, this is like an old mine shaft that people used to mine iron or copper or something like that. And flowing out of it is some water, and that water looks very gross. It turns out that most mines, because of the minerals that are inside the mine, specifically this mineral here, FeS2 or iron sulfide, this is sometimes called pyrite. This mineral, when it reacts with water and oxygen, and this is all details, produces an acid. And you can see that as because one of the products is an H+, and we know that H+ is what produces an acid. So the water that leaks out of these old mines is polluted, essentially, with acid. And that's a problem because as these get abandoned and there's not a lot of upkeep happening, this acidic water then goes into local streams or rivers, and it can cause problems with wildlife, water quality, the ecology, and it leaves these mineral deposits everywhere. It can be a bit of a problem. And so the question is how to get rid of this. How do I get rid of this acid pollution? Is there a way that I can eliminate this acid without introducing other dangerous chemicals or without properly, accounting for the wildlife and everything else? So to take a step back from this major problem, let's look at a smaller problem that happens to us in our everyday life. What do we do if we get too much acid inside of us? You can see a picture of this man who's maybe eaten one too many spicy foods. Well, we typically will, or we can take what we call an antacid, something like a Tums, or this is milk of magnesia. Both of these are actually chemicals. I know you might be spooked because chemicals, but these are chemicals that are designed to neutralize the acids in our stomach. So these are essentially bases. Milk of magnesia, for example, is magnesium hydroxide. Typically Tums is like calcium carbonate, but the point stands that these are chemicals that will neutralize the acids in our stomach. And what does it mean to neutralize? Is it killing it or destroying it or blowing it up? Or just is it more making it less dangerous or less powerful? Well, if we take a look at the chemistry, you'll see that there's actually something really, really elegant going on that just has, it's just so beautiful when it all clicks, if it clicks. So really, neutralization is just using the power of acids and bases to cancel each other out. But how do they do that? This equation is really where it's at. So that H+ that I talked about before in previous videos that is significant, or signifies an acid, if it gets added to something that's a base, typically that's something that has a hydroxide at the end, that H+ and the OH- add together, they stick together essentially to each other. So the H sticks to the O, which is stuck to the H, and you get like an H and then the OH or an HOH all stuck together. But if you look upon closer examination, that's the exact same thing as H2O, which is just water. This makes perfect sense. Of course, if I wanted to neutralize an acid, I would want to do a reaction that creates water, because water is neutral. And similarly, if I had so much of a base, I would want to be adding an acid to it to neutralize that base and create water, again, which is neutral. So in the case of this acidic mine that's draining all this acid pollution out into the rivers, or in the case of us, when we eat food that's too spicy or acidic, the goal will be to cancel out the acid. We need to add the exact same amount of base. And it's so elegant a solution, and it's done all throughout chemistry. And it really rewards us for understanding at the molecular level the difference between these particles in solution, floating around, concentration, and all that jazz. So what would happen if we overdid it? What if, for example, you took way too many of these antacids? Well, then instead of your stomach getting neutralized to the appropriate, the appropriate amount, it might become too basic, which is a problem too. Of course, you don't want to be eating, drain cleaner or something like that to neutralize a stomach ache. That'd be way overdoing it. And similarly for us, if we're trying to solve this acid mine problem, if we add way too much base, well, we get the opposite problem. Instead of our creek being a little bit acidic, it becomes really basic. And that really basic solution, it has many of the same, if not worse, problems on wildlife, water quality, and everything else. But when I say we need to add the exact same amount, what do I really mean? Do I mean the exact same amount by mass? Well, that's pretty tough because maybe I have I have a whole water flowing out of this creek. It's not necessarily easy to measure the mass of it that's the acid. What about the volume? Well, if you've learned about concentration, you know that volume itself doesn't always reflect how many chemicals are dissolved inside of it. If I have a really concentrated solution, I don't need much volume, versus if it's just really weakly acidic, then it would take a very large volume before I have very many. So it's not really clear how we're going to add the same amount of two different things. I encourage you to look back at this video if you haven't, where I make a 1-to-1 solution of salt and sugar. So I did this video before we had learned about acids and bases. It's possible you haven't watched it yet. I would encourage you to go ahead and watch it, where I go through the steps. But if you just want the main point, essentially, in order to get the same number of particles of acid and base, so I want the exact same number of H pluses and the exact same number of OH minuses, we have to make sure we have the same number of moles in the solution. Oh, there's a bit of a typo there. And so in order to get the same number of moles, we're going to have to pay attention to not only the volumes, but also the concentrations of our solutions that we're adding. So again, the goal being we want the same number of H pluses and OH minuses because every H plus paired up with an OH minus basically neutralizes the threat. By itself, an H plus is dangerous. By itself, OH minuses are dangerous. And of course, what I really mean is large groups of H pluses or large groups of OH minuses. But if I can get just the right balance, then it all kind of evens out. So what we call that, when we have the same number of moles of acid and base, we call that the equivalence point. So not equilibrium, which maybe you studied before. This is equivalence, and we're really talking about an equality between the moles of acid and the moles of base. Now, you might be wondering, well, moles of acid, that's great, but if Mr. Kramer, we talked about this, I can't measure moles directly. That would require me going in there and counting 1, 2, 3, 4, 5, 6, all of the H pluses in the solution. Not only would you have to count until you were long dead, but you'd need a microscope that can see the individual H's floating around, and that's very impossible because they don't look like the letter H. They're actually tiny, protons essentially floating around the solution.